like this entire section as your formula. So you'd have everything, but you still need to know what all this stuff means. And there's a lot of U's. So U of T is representing the temperature of whatever's cooling. So if your soup is cooled to 80 degrees, that's what it's representing, the 80 degrees. U sub 0 is our starting temperature. So if I pull it off the stove and it's 200 degrees, that's my starting temperature of the soup or whatever it is, or T. Capital T, right here in the equation, two different places represents the temperature of our, basically the surrounding media. It could be the temperature of the refrigerator, the temperature of the room, because we talked about something that's cooling down. When it starts to reach room temperature, it can't go below room temperature, right? It's got to plateau at room temperature. And little t, C e to the kt, that's that part of the formula we've been working with yesterday or Tuesday, right? Because we've been working with the formula A equals A sub 0 e to the kt. See how this part is in Newton's law as well? But there's a couple other things impacting the cooling. The starting temperature, the temperature of the room, and that's basically it, I guess. So Danny boiled water for tea. So that's actually part of the given information. Do you know what temperature water boils at for Celsius? It is 100 degrees even for Celsius. This problem is all in Celsius. If you have it all in Fahrenheit, you can still use this equation without translating it if it's all in Fahrenheit. So you have to be all in Celsius or all in Fahrenheit. So I would give it to you that way. I'm not going to trick you with Celsius and Fahrenheit and convert them. So he boiled water for tea. That's the original temperature of the water. After waiting for 3 minutes, Danny found the temperature of the tea to be 60 degrees. That's how fast it cooled. Danny likes his tea at 40 degrees Celsius. How long should he wait before drinking his tea? Assume room temperature is 21 degrees Celsius. That's about our 70 degrees, like our comfortable room temperature. So we do not know the K value for this mug or this tea, right? How fast is it cooling? So we're going to do the first part of the problem to calculate our K value. Then we can redo the problem and say how long he has to wait for it to get to 40 degrees. A restaurant might need to know this. Like when they ladle the soup into the bowl, they want it to go out hot, right? So they might not want to scald the person's mouth, but it might be important to know how hot the light is, like under the warmer, so that the food is still going out hot. So it might be more relevant for a restaurant situation. All right, so what do we know? We know the tea cooled to 60 degrees. That's our U of T. That's the temperature of the tea currently. This is a little bit blurry. Let's see if I can fix it. He waited for 3 minutes. That's our time. What do we need next in the equation? Capital T. Capital T is the temperature of my room. So 60 equals 21. That's capital T. Plus parentheses. U sub 0, that's my starting temperature. So that's 100. I'm just following this equation, minus the surrounding media, so minus 21. And then e to the, I don't know K, but the time was 3 minutes. So I have to be able to plug stuff into that equation and solve for K. So we've got to know order of operations. What should I do first for order of operations? Parentheses, right? So 100 minus 21, is that 79? Okay, so that's 79. This is 79. What's my next step? Ohm? Yeah. 100 is the starting temperature. The tea boiled to 100 degrees. So I said it's kind of, this one was a little bit of a hidden piece of information. You have to know that water boils at 100. I mean, I could probably tell you that on a quiz or a test. The starting temperature is, blah, blah, blah. But that's a good application of science, knowing what temperature. What is it for Fahrenheit? Is it 212? No. Fahrenheit? Why do I think it's 212? Okay. My next step. Here's a big no-no. Do not combine the 21 and the 79. The 79 is being multiplied by E to this power. The 21 needs to get stripped away to the other side first, right? This is all connected still. The 21 is what you want to subtract to the other side as your next step. So that would be what? 39 equals 79e to the k times 3. That's a really important order of operations algebra step, that you're going to subtract this 21. You don't get to combine the 21 and the 79. What's my next step? Divide by 79. I'm just going to leave it as the fraction 39/79 rather than making a decimal. Okay, I'm in exponential form, and the exponential part is now by itself, right? So what do I do next to solve an exponential? Put it in log form, yes. So my log is going to be base e, which is the natural log. I could just write that ln if I wanted to, of 39/79 equals k times 3. I was going to write it in the other order, but. So I'm taking the natural log of 39/79 on my calculator, and then I would divide by 3 at the very end to get k. I kind of took up a lot of room because I haven't even solved the whole problem yet. But, all right, so I take the natural log of 39/79. If you don't have a calculator, I put them all in the doc so they were charged for SAT, so you might need to go grab one because not everyone used them yesterday. So after you take the natural log, you're going to divide by 3. And you should have a negative k value because you're decreasing in temperature. So write your k value down. I would leave like, I don't know, 3 or 4 decimal places. Did you get 0.2353 about? Negative 0.2353 is k. Here's what I typed in. The natural log of 39/79, enter, divided by 3. You could also do the log base e if you wanted to. Didn't get it? Did you type the log key or the natural log key? Oh, you have to do the natural log of it. Not just 39/79. It's the log of 39/79. All right, so now we need to know how much longer it's going to take. You could type it into the y equals menu. You could solve it using logs. You could guess and check. So there's kind of multiple approaches to this next problem. I just set it up the same way I just did this problem. What does he want? He wants it to cool to what? 40 degrees. So he wants his end temperature to be 40 degrees. The room temperature is still 21. It says how much longer should he wait? So it currently is 60 degree T, right? It's cooled to 60. How long should he now wait to get to 40? I put the minus 21 in there, E, to that negative 0.2353, and I don't know my time. So you're basically doing the same exact steps with just slightly different numbers. So see if you can figure out the time it would take. So strip the things away using order of operations, change it to log form, and solve for little t for time, just like you solved for k in the previous steps. My video here. Here is the answer to that. He should wait 3 more minutes. So now we're going to look at number 4 on the next page, the pizza, and we're going to put up our answer in a minute. Unpause here. So I used my k value of, here's my k value calculation. So k came out to negative 0.1004. And then I started at 300 degrees and I solved for t, so 12.6 more minutes or 17.6 minutes total. Take a look. If I was going to set up example 3, we did 3? See, I think that is me writing number 2. Okay, I don't remember doing 3, so if you already did it, turn to the back page. You can work on 5 while we're doing 3. Maybe you just did 3. I don't remember doing it, but so here is the important part. The half-life of radium is 1,690 years. That's the information that you need to find K first. Then you're going to use that information. It says if 10 grams are present now, how much will be present in 50 years? So it's going to be pretty close to 10 grams because 50 years is like a drop in the bucket compared to 1,690. So not very much time has passed for this radium. So to set up a half-life problem, you use the A equals A sub 0 E to the KT formula. So I would give you that formula on a test. You don't have to come up with it, but you have to know what to put in for each piece. This is my initial amount. This is my half amount because it's a half-life problem. So you could put 10 grams in if you want, because that's what you're going to put in for the next step. So if you put in 10 grams, it's telling me the half-life is 1,690. So I'm going to put that in for T. What is A after the half-life? If I start with 10, how much would I have left? 5 right here. So I'm making up these two numbers for the initial and the half-life amount. That's a 5, by the way, not a 6. So you would solve this first for K, then you'd use your K value to figure out how much is present in 50 years. So why don't you try solving number 3 and I can check your answer and then move on to the back page. You don't have to do a super graph on the back page. You can skip the graphing part and just see if you can answer the questions using your calculator. So see if you can finish 3 and 5 so that we're really done with 121. And then there's some just more practice on application problems and interest for tomorrow. And we're going to do some review tomorrow. All right, and you do have homework tonight. Your homework tonight is log number 3 homework. I'm not sure what day that is on in your agenda because I've moved it around, but number 3 is due tomorrow. And then number 4 is not due till next week. So you've got Friday, Saturday, Sunday, Monday, Tuesday. I see you on Wednesday. That's really quick. So we got a K value of negative 0.0041. And then when we plugged it all in, we got 9.79 grams. And we're going to start next time with example 5.